Hello. Okay, so everything should be set up now. Can you hear me and do you see the desktop? Does everything seem okay?
Yeah.
Okay, great. Thanks. All right. So we're you know, on class of the day we did this one example of a higher order function. Okay. It was an example of a kind of higher order function. It's uh, a function in the case is like sorting, but it took a comparator. So we did this function extreme. Yeah, it took as an input a comparator function that decided which is the larger of two items. But we call it extreme because it could be the comparator could be finding max, it could be finding min. So this is one example of a higher order function, a real famous example. Yeah, and it generalizes the idea of sorting. Okay. Now today we're going to do some more examples of higher order functions. But first I want to do something called curried functions. Okay, so in the outline of this chapter, there's this thing, higher order functions and currying. Okay, currying is a really tricky idea. We want to introduce currying because we want to use it, but we're going to just see how to read it and see how to use it, and then we'll come back to it and see how it's created, how it works, like what's the mechanism for doing currying. So what I want to do today is introduce currying so that we can use it in more examples of higher order functions. In fact, we are already using it in this example we did the other day in extreme. We were already using curried functions in this example, but I never really explained what was being done differently here than before. So let's carefully do currying. Okay. Well, when I say carefully, I mean let's see how to read currying and use currying, and then we'll talk later about how it's implemented. So we're going to introduce currying, go back and do more examples of higher order functions, do these predefined higher order functions, and then go back and see how currying works. Okay, so we're going to introduce currying, then we're going to go back to higher order functions, do more examples of higher order functions, and then go back to currying and see what makes it work. Okay, so let me uh, create some example. Well, actually, let's see what's the best way to do this. Yeah, let me just create a file of examples. Okay, okay. So I'm going to define a couple functions. So function f1 is going to take an x and a y as input, and it's just going to take the product of x and y. Okay, real simple function. Okay, I can put that into SML. Okay, and it just multiplies. See, it looks like Java. 3 times 4. F of 3, 4 is 12. F of 5, 6 is 30. And this looks an awful lot like Java. Yeah, it looks like I'm using Java notation, but ML doesn't use Java notation. I'm really kind of abusing the notation of ML here. I really should write this way for one thing, okay? Because in ML, a function doesn't need parentheses. These parentheses are not part of the function call. They're part of the tuple. Okay, so here's the thing. F1 is not a function of two variables. F1 is a function of one input. Okay, so this is a function. This is a function with one input parameter. Okay, not that it looks like it, but it has one input parameter. The input parameter is this tuple. Okay, now here, let me define another function. Okay, F2 is going to take a tuple, x and y, and another tuple, u and v, and it's going to create, I'm going to compute their dot product. So I'll take x times u plus y times v. So there's a dot product, actually. That's the dot product of two vectors, okay? Now, this is going to be a function of two parameters. Okay, now this is going to stop looking like Java, okay? Over here, I'll go ahead. Here's the function definition. Now, F2 takes in one tuple, then it takes in another tuple. Okay, it's not a function of four variables, it's a function of two tuples. Okay, so it took 1 times 3 is 3, 2 times 4 is 8, 8 plus 3 is 11. Okay, so notice I don't write it as, now if this was Java, I would be writing something like f of one input, then another input. Yeah, that's kind of like what, but then that would be, okay, let me define another function here. F3 takes in a tuple of tuples. Okay, and then it's going to have the exact same right-hand side. Okay, this is a function. We're back now to a function of one input parameter. Okay, there's four numbers in there, but the four numbers are bundled into a single tuple of two tuples. Okay, and then that would be this notation here, even though this would be F3. Oh, I haven't defined F3 in ML yet. I forgot to copy it over there. So here's F3. Whoops. What did I do wrong? Anybody see what I did wrong here?
There's no fun.
Oh, I've done that before. Yeah, I forgot to put the fun in front of there. So I go back over here. Okay, put the fun in there so that I don't forget it again. And then I can come down here and just there. Okay. Now, okay, here's F3 of 3, 4, 5, 6. Okay, it looks like I'm using Java notation. It looks Java-ish, but it's not. That's not, okay. That should be thought of as one input. That input is two tuples. It's a tuple of tuples. Okay. All right. Okay. So now I could do another example. Fun F4, and I'll make this a tuple X, Y, U, V. There's only one input, and I can give it the exact same right-hand side. Okay. This is a function, still a function of one parameter. Okay. Notice how many different ways ML can let you define things. That's still a function of one parameter, and I would call this F4 with the quadruple 3, 4, 5, 6. Okay, so that's it's treating this as one two vector, and this is another two vector, and it's treating them and computing their dot product. Okay, so I get the same input. I get the same result that if I called F3 with the tuple 3, 4 and the tuple 5, 6. Notice I just put extra parentheses. Okay, this is one input that's two tuples. This is one input that's a quadruple. Okay, so I'm not using currying yet. I'm using tuples. Okay. Okay. Now, this was a function of one input. This is a function of one input. This is a function of one input. Okay. This one is one that's curried. See, this has got two parameters. Functions with more than one parameter in ML are curried. So let me pull this one out and change the order. This one is a curried function. All these were one parameter, one parameter, one parameter. Any function has more than one parameter in ML is actually a curried function. So there's one parameter, and notice that you don't put any commas or anything, you just put a space, and there's the other parameter. Okay, now here, let me take this function and make the curried version of it. It would look like this. I'll call it F5. It takes input X, Y. Okay, that's the curried version of this. It takes really two parameters, and it just takes X times Y. Okay, so F1 doesn't take two numbers. Okay, if you go back over here and compare F1 and F5, okay, F1 looks like it takes two numbers. And F5 really does take two numbers. So they both give me the same. But F1 is really taking a single pair, and F2 is taking two inputs, two different numbers. Okay. Now, here's one way to see that F1 really takes in one thing. Okay. Let Z be the pair 3, 4. Okay. F1 can take that. See, F1 works on Z because F1 really only took one thing. That thing was a tuple. So F1 really is a function of one thing. Now, F5 doesn't know what to do with Z because F5 isn't supposed to have a pair. It's supposed to have two numbers. So F5 is going to say Z doesn't work. Okay, because see, F5 was supposed to take in, well, notice that the error message is kind of weird. The domain was int. Notice the domain, we thought of as int, but ML actually tells the error message that F5 took in int. Because what this really is going to amount to is that F5 takes only in X. And then we'll see later on that F5 only has one input, which is X. And Y is kind of funny. Yeah, we'll say later what's really going on here. So ML's error message is that the domain, the input to F5 was supposed to be int, but it got pair of ints. Yep. Okay. Now, if we ask ML about F1, ML says it's a function that takes in a pair of ints and gives us out an int. Okay. F5, if we ask ML what it is, it says it's a function that takes in an int. And then notice that then it says, well, this is its way of saying, and then it takes another int. But ML actually reads this kind of oddly. We'll see exactly how it's reading it. The function actually takes in one int at a time. And after it's taken one int, then it's ready to take in another int. So that's why it says that its domain is just int. Because first it needs to get one int before it can take in the second int. Okay, this is what's called currying. It takes some real getting used to what's going on here. So what you have to think of, what you have to remember is that in ML, Functions that take in more than one parameter, like this, are curried, and the parameters don't have parentheses around them, and they don't have commas in them. Okay, so you use F5 on two numbers by just saying F5, a number and a number. Okay, that's what it means for a function to take two inputs. The inputs are separated by spaces. Anytime you wrap things in parentheses, you're actually using a tuple. And that's only one thing. That's one thing. That's not two numbers, because it's not Java notation. That's not the same. It's okay to write it that way, but boy, it causes so many people to misread this, to think that that's like Java. Okay. Yeah, and then you'd think that F5 might be written the same way. So you'd want to do F5 of 3, 4. And that's not how F5 wants to be. See, F5, now it's back to saying, no, I take in an int, but you gave me a double, a pair of ints. F5 is supposed to take in an int, but it was given a pair. It was given a pair. Okay. 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 See, and it didn't matter if I put the space there or not. The space doesn't really mean it. It doesn't actually. The space there doesn't mean anything in Java either. When you call functions in Java, you put the name of the function, parentheses, then the parameters. Okay, but you don't actually have to write it that way. You can put as much space as you want between the name of the function and the input parameters. This space here doesn't mean anything, even in Java. It just kind of, it's traditional to write it like that, but it doesn't need to be written that way. Now in ML, the tradition is to write always the name of the function, first parameter, space, second parameter. Okay, the function should be F5. The name of the function, space, parameter, space, parameter. Okay, so even if I'm calling F1, I should put spaces, then the tuple. Okay. Okay. So name of the function, space, then the input, whether the input's a tuple or not. Okay. All right. So this function takes in one tuple. This function takes in one tuple, but that tuple is a tuple of tuples. Okay. This function takes in one quadruple, still one parameter. If I go back here to F4, I can let C is the quadruple. Okay, so C is a quadruple. Now F4 takes in one thing, C. Okay, and here I can see that it's really taking only in one thing. I gave that thing a name, and it only took one thing. Now you can't do this with F5. F5 takes in 4 and 5, right? Like that. There's no way that I can have, say, the letter P. I can't say val P equals 4, 5. That's not a data structure. That's not a thing that you can give a name to. Okay, so ML complains about that. See, that 4 space 5 is not one thing. There's no way I can give a name to 4 space 5, like I can give a name to a tuple. See, I can give it, that's one thing. From ML's point of view, that's one data structure. That's a value that I can give a name to. And then the function took in that one thing. And here I was using a name to refer to it. That's not in any way one thing. That's two things. And you can see that you can't somehow give it a name. You can't give 4 space 5 a name. It's not a data structure. Okay, it's just the number 4 with a space after it, followed by the number 5. It can only be used in a situation like this, where I have a function of 2 inputs. That's the first input. That's the second input. I could easily give 4 a name, and I can give 5 a name, what did I do wrong here? Oh, I forgot the equal sign. I give 4 a name, and I give 5 a name. Okay. Then I can call F5 on the names X and Y, but see, it's still taking in 2 things. I can give them names, but with tuple, when a function takes in a tuple, it's only taking in 1 thing, so you only need 1 name. When this function takes in a tuple, I can give, it's just 1 thing, so I only need 1 name. If I wanted to give that tuple a name, I only need 1 name for it. Okay, so currying means when a function actually takes in more than 1 parameter. If you're using tuple notation, you have to be careful and just make sure you remember that this is a function of 1 variable, that's a function of 1 variable, that's a function of 1 variable, but the variable's been pattern matched to its constituents. Okay. Here, let me redefine F1. I'll do it just below. Here's another way to write F1. Function F1 of, I'll call it X, is, okay, well, what's X? It's supposed to be a tuple. So I would take I would want the first thing out of that tuple, and that's written #1 of X times #2 of X. So there are the pieces of the tuple. See, it's still only taking 1 thing. Here I'm using a pattern to say that the 1 thing is a tuple, and I want to name X as the first thing in the tuple and Y as the second thing in the tuple. But the function is taking in 1 thing, this tuple. Okay. Here I'm saying the function takes in 1 thing, and it's a tuple, and there's the first thing in the tuple, and there's the second thing in the tuple. Now, this actually won't work in ML. It's not quite written properly. If I take this one and type it into ML, ML is going to give me a little bit of a complaint about it. I'll show you why. ML was really designed to be done using pattern matching. So this style of programming doesn't really actually work very well. Here's the problem. Let me define a function F1 prime. It's going to be a slightly different version of F1. It's going to take an X, a Y, and a Z. So it's a triple, not a tuple. And it's going to take the product of X and Y and Z. Okay. Okay, that's fine. That's easy enough. Okay. But now, suppose I want to write it in this style. Well, then F1 prime would take in 1 thing. It's a triple, so it's going to take the first thing in the triple times the second thing in the triple times the third thing in the triple. Now, the trouble is ML doesn't know if this is a double, a triple, or a quadruple. There's nothing that told it that it's a double, a triple, or a quadruple. Here, there's nothing to tell if it's a double, a triple, or a quadruple. So ML doesn't like this notation unless it knows ahead of time how big the thing is. Okay. So something has to tell ML that this is actually really a double, a pair, and that this is really a triple. Okay, if I go over here, #1 of 3, 4. See if this works. See, that was 3. #2 of 3, 4. Now, but that works because ML knows that's a pair. Okay, ML knows it's a pair. Now here I can say #1 of 3, 4, 5. Okay, #2 of 3, 4, 5. But ML knows that the thing after the #1 is a triple. So I can do #3. Over here, if you look at that code, what if I did this? That would be a function that would, well, actually, I'll go down here. Suppose I don't use the y in my answer. I just take the product of x and z. So in this line of code, ML has no way of knowing that this is a triple. I mean, you could look at that, but for example, I could do this even. So it's a quadruple, but I'm using the first and third of the quadruple. ML has no way of knowing that here, that I really want a quadruple, but I only want to use the first and third of the quadruple. So this one shows you why ML can't use this notation on the right. It actually has no way of knowing what I'm really doing over here. Is that the first and second of a double, or the first and second of a triple, or the first and second of a quadruple? Is this the first and third of a triple, or the first and third of a quadruple? Okay. Now you can fix this by telling ML here the type of F. You would say that X, you actually have to, this is one of the few places in ML where you have to say that the type of this is int times int times int times int. So I have to tell ML that it's a quadruple. So I tell ML that it's 4 ints. Okay. Here it's pattern matched. See, ML really prefers pattern matching. Here it's pattern matched. But see, the key is that this shows me it's really only one input. Okay, so this now, I can do this. Okay. And then I can say F1 prime of the single input. Okay, now it's going to multiply the what is it? The 1 and the 3. Okay. Or if I do this, okay, what's it going to do? It's going to multiply the 4 and the 2 to give me 8. Okay, all right. So there's two things to see here. First, that this is a function of one input, a quadruple, and I could actually use a single variable there. But on the other hand, when I work with tuples, ML doesn't like me to use, it doesn't really like this notation. So you have to kind of really work hard to be able to use that notation. ML cannot by its, if I don't do the typing, if I do it the wrong way, so this one is wrong. If I get rid of the typing, it's wrong. ML has no way of knowing what X is. It can tell it's, because you use this notation, it can tell it's a tuple, but it has no way from this right-hand side of figuring out, is it a 3 tuple? Or you might think, well, it's a 3 tuple because you used index 1 and index 3. So, okay, it's a 3 tuple, but in fact, we meant it to be a 4 tuple. We meant it to be a 4 tuple. So you have to tell it that, okay? But the key is that this is not a curried function. It's a function of only one input. So this is not a function of 4 inputs. Okay, this one is not a function of 4 inputs. It's a function of one input, a quadruple. Okay, now if I want to write it as a function of 4 inputs, I can write it this way: function. I'll write it now f1 prime of x, y, z, w, and the result is just going to be x times z. Okay, that's really a function of 4 inputs. I don't use 2 of them, and I take the product of the first and third inputs. Okay, but that's curried. Okay, that one really is a function of 4 inputs, not 1, 2. See, okay, that's a function of, whoops. Oh, yeah, ML's real clever. Since I didn't use the Y and the W, ML polymorphed them into type A and type B. So my function took in an int, an arbitrary thing, an int, an arbitrary thing, and gave me back an int. So ML actually was figured out. See, it actually figured out the Y and Z, since the Y and W, since they weren't used, they don't have to be ints. Okay. And actually I could have done that over here too. I could have even said here, oh, I don't really care what Y is. So I could have put here, oh, it's a type A. And I could have said, I don't really care what the fourth thing is. I even could have said here, it's a type B. I could have said that in my own definition. Okay. So it's up to me whether I want to make it polymorphic or not. Okay. I'll leave it like that. But if I do it this way, as a curried function with 4 inputs, and I don't give types to the inputs, ML makes it polymorphic. So now f of 2, 3, 4, 5 is going to multiply the first and third of them. Whoops. Oh, it's f1 prime. Okay. It multiplied the first and third of them. 2 times 4 is 8. Okay. So curried functions are functions that take in more than one parameter. Okay. You gotta be careful to distinguish functions that take in a tuple from functions that are curried. So for example, this one's curried and it takes in 2 tuples. So let's go back to this one and play around with it a little bit. This one is curried. Okay. It's a function of, there's the first tuple, then it takes in a second tuple, and it gives me out an int. So you read this as a function of, you go up to the first arrow, that's the first input, a tuple. Then after the arrow would be the next input, another tuple. Then the last arrow says what the return type is. So it takes in tuple of integers, another tuple of integers, and gives me back an int. So it only takes in 2 inputs. Okay, so F2 takes in 3, 4, say, and 5, 6. Okay, now I can give a name A to 3, 4. Then I can give a name B to 5, 6. And then F2 takes in A and B. It only takes in 2 inputs. Whoops. Oh, I forgot the equal sign on the val B. So my mistake was right there. I forgot the equal sign on val B. Okay, so fix val B. Okay, now do F2 of A, B. See, F2 really is a function of 2 inputs, but tuple, tuple. Okay, right? So we got to be very, it can get tricky and confusing. Once you're used to it, it's very elegant. Now I'll show you in a second, like what makes it so elegant, but it actually works out very nicely in a certain way. Okay. A lot of people like to program with tuples. So a lot of people, even people who are used to ML, if they have a function like F1 that takes in 2 numbers and multiplies them, they're just as likely to find it this way as if they were to define it this way as curried. Okay. Almost no one would ever write that. Okay. Again, that one won't work unless you put this one as it's written is wrong because it doesn't have the type. ML doesn't know that that's a tuple. Okay. So to make it correct, you have to tell ML that this is a tuple, not a triple or a quadruple. Okay. So, the ML prefers pattern matching. If you don't want to use pattern matching, well, that's a function of one variable. Then you can pull apart the value, but not if in this case, because of the funniness of tuples, it doesn't know how big the tuples are. I need to say how big the tuple is first. Okay. Okay. So almost always use pattern matching in ML. There's almost never a case when you actually want to write a function this way. If the function takes in a quadruple, write it as a quadruple pattern. If the function takes in a pair, write it as a pair pattern. So for example, F3, if I wanted to, I could write this in a real weird way. Fun, I'll write it as F3 prime. It takes in a U and a V, okay? But U is a tuple and V is a tuple. So this would take the first item of U times the first item of V, that's the first part of the dot product, plus the second item of U times the second item of V, okay? But ML doesn't know that these guys are tuples, so then I have to go back over here and say that this is a int times int pair, and this one is an int times, well, actually, I think I have to put the parentheses, I should put that parentheses should be there. U is a pair of ints, and V is a pair of int, okay? This is a horrible way to write ML, okay? This F3 prime is the same as this F3. Okay. Oh, no, I'm sorry. This one, I'm sorry. I'm actually writing this F2 down here. I'm sorry. This F3 is a pair of pairs. So what I'm writing, this one belongs down here. It's F2 prime. Okay, it's the bad way to write this one. This one takes in two things, a tuple and a tuple. So it's a function of two parameters. Calling one of them U and call one of them V. There's the two parameters. But since they're tuples, I have to declare them as tuples. Okay, so these two, I'll go ahead and okay, so F2 and F2 prime are the same. So they have the same type. They take in, the first thing they take in is a pair of ints. Then they take in another pair of ints, and they give us out an int in return. Okay. This F2 is written the right way. This F2 is written in a horrible way, but it's still a function of 1, 2 inputs. Here, you got to be careful. That's not a function of 4 inputs. It's a function of 1, 2 inputs. The space here with no comma is the thing that tells you that's a curried function. See, it's F2, see the way it's written, the name of the function, space, first parameter, space, second parameter. The parameters are separated by spaces, okay? In ML, curried functions, which are functions of more than one variable, their parameters are separated by spaces. If you see commas, there's tuples involved, okay? So that's all one parameter, one single tuple made up of 2 tuples, okay? This is one single parameter that's a quadruple, okay? So ML takes, you can think of ML as like having almost 2 kinds of functions, tupled functions and curried functions, but occasionally you'll hear people say that. You could have a tupled function or a curried function. See, the tupled xy or the curried xy. So this F5 is like, this is the tuple version of the product at x and y. This is the curried version of the product in x and y. But that's not a good way to think about it. Don't think that there's 2 kinds of functions, tupled functions and curried functions. Some people explain it that way. You'll never see it explained that way in a university course, but if you read blog posts, you might see people saying it that way. People who really know the language would never say that that this is a tupled version, a tupled function. This is a curried function. This is just a function that takes in one parameter that is a tuple. This is a curried function of two parameters. But there's two very distinct ways of writing the function. And some people, in many cases, people prefer it this way. You know, depending on how you're writing your code, you may say, oh, this is perfectly good. It's actually, I may prefer to write the function this way than this way. Now, this one's got a kind of a funny advantage. Okay. Let me give them different names. I'm going to give them, I'm going to call them F and G. So I'm going to say function F is x, y equal to x times y. I want to simplify the names a little. So there's function F and function G of x, y is x times y. So there, if you want, there's the tupled version and the curried version. Okay, I want to compare them. There's a little bit of difference between them. I can do something interesting with this guy that I can't do with this guy. Okay, so the tupled version is a little less versatile than the curried version. And this is why ML has currying, and this is why people prefer currying. So I'm going to give ML these two. Whoops. Okay, here's the tuple. My control, I still have this broken key on my keyboard. I haven't figured out how to fix it. So a lot of times when I do Control C for copying, it doesn't work because the control key is broken. Yeah, see, it's still broken. I'm not. I have to resort to copy and then paste. Okay, there's F, and then if anybody knows how to replace keys on a laptop keyboard, I know how to place keys on old-fashioned, like separate keyboards, but I have no clue what to do to replace a key on a laptop keyboard because everybody's laptop keyboards look different. I don't know if I have to, I mean, if anybody knows, like, you can send me an email, but I have a feeling I have to like somehow go to the manufacturer of a laptop and ask them if they sell individual keys. I'm afraid that's what I need to do. Okay, all right, there's F and G. So F is a function that takes in a tuple and gives me back an int. And G is a function that takes in an int, then takes in another int, and then gives me out an int. So you see the difference in the tuple as a single input. See, there's only one arrow. So that tells you there's one input and the output. Okay, now there's two arrows here that actually you read that as the inputs are int followed by int, and then the output is an int. The last arrow tells you what the output is. The last arrow tells you what the output is. The other arrows tell you what the individual inputs are. So int, int, okay? So you call F with a tuple, and you call G with two numbers. So you call G with two numbers. Okay, but here's what you can do. It's interesting. I'm going to call a function G with 4. G with 4 is G4. What I'm going to do is I'm going to give G only one of its inputs. See, it took an input. See, that's why this arrow's here. You could give it that input and not give it the other input. So here I'm going to give, whoops. Oh, I forgot the fun in front of it. I'm defining a new function, G with 4. That's G with one of its inputs only. Oh. What did I do wrong here? Oh, no. Oh, I know. I don't use fun for this. I use val. There. Yeah, it's kind of court. I should use val, not fun here. Okay. G with 4 is G with just one of its inputs. This is called a partial application. So if I go over here, I'll write it here. Val G with 4 equals G of 4. This is called a partial application of a curried function. You can only do partial applications of curried functions. Okay. Now, what does that do? That essentially gives a 4 here. So now this G carries with it the 4. So it's going to take 4 times anything else I give it. So now I'll go down here and I'll say G with 4 times 5 is 20. G with 4 times 6 is 24. So G with 4 carries one of its parameters already given to it. Later on, we'll see that you can do very clever tricks with this. When you have curried functions, you can give the curried function one of its parameters and then give that a name. So this is the name of the curried function with one of its parameters. And then that can be very useful. Now, actually, we saw this last week. Okay, go back to when we did the extreme case. We did this trick kind of in a neat way here. Let me show you how we did it. Extreme is written as a curried function. See, there's no commas there, just spaces. So I wrote extreme as a curried function. It takes in the comparator, and then it takes in a list. And it finds the extreme of that list using the comparator. Now, down here, see, I called the max function is extreme with just the comparator. So if you say compute extremes with the greater than symbol, that's what we mean by max. Okay, so there's an example of a partial application. And this is actually how many library functions are done. In ML, you have this really interesting style of programming that you can write a very general purpose curried function. And then by giving it one of its parameters, like the greater than or less than, you can build other library functions. So max is a special case of extreme, and min is a special case of extreme. Max is extreme with that comparator, and min is extreme with that comparator. And all I have to do is write this little bit of code, say, give that comparator to extreme and call it max, give that comparator to extreme and call it min. Okay, so that saves me from writing. See up here, this was writing max completely out by, there's the full-blown definition of what max is. Okay, so there's max, there's min, and then here's extreme. But because extreme is curried, I don't even really need these definitions of max and min. I can recover them from extreme by this really clever trick of saying, okay, partially apply extreme, which is one of the parameters. Now max is waiting for the other parameter of extreme, which is the list. So now max will find the max of any list, because extreme got one of its parameters and it's still waiting for the other one. So this partially applied function is still waiting for the list part. Okay. All right. So that's what's happened over here. This is function. It's got it's G with one of its parameters. You can't do that with tupled functions. Okay. There's no way to give F half of a tuple. There's no such thing as half a tuple. Okay. Now I can do the following, and you'll see. Okay, I'm going to create F with 4. Here's a way to create F with 4, and I can even do this in Java. Fun F with 4 of y equals F of 4 comma y. So what did I do? I'm building F with 4, just like I built G with 4. But look how, I have to do it in a much more complicated way. I want to give this guy the value 4, and then let this be the other parameter. So I say f with 4, oh, it takes in one input. But then it calls f, see, I have to actually explicitly call f with the 4 in the tuple, and then there's the parameter y, okay? Okay, some people will actually refer to this as a partial application of f, and you can do this even in Java. You can do this in Java, but there's nothing elegant about it. You're just saying, okay, f, I'm hardwiring one of its inputs, and you're giving me the other input. So I call f with one of its inputs. That's nowhere near as nice as something like this, okay? But this is still in a sense, this is kind of a fake version of partial application for a tuple function, which is exactly, I mean, again, you can do this even in C++ and Java. Yeah, if you've got f and it takes in 2 inputs, and you want a version of it that takes only 1 input with 1 parameter given as a default value, you can write this. Oh, there are some languages that let you do the following. You can't do this in C or C++, you can do it in Python. You can write something like this. Fun f, right, okay, right, fun f. I'll write this in kind of a Python-like notation. I'll write it this way. Int f of int x equal 4, comma, int y. The return value is return x times y. Java doesn't let you do this yet, probably never will, but a few languages let you do this. This is referred to as a default value. Now what that means is if you call f with 2 parameters, x is 3, y is 4. But if you call f with 1 parameter, x is 4, and then this one's y. Okay, so that's kind of like f with 4. Okay, but it's using a default, what's called a default parameter. So this is essentially f with 4 because f's got this default parameter. Okay, there are languages that let you do that. Now in ML, you have to give this thing a new name. F takes a tuple. Okay, f with 4 takes only one number. Okay, like this. There are no default parameters, but this would be Python-like. Okay, this isn't valid ML. Okay, but Python has something like this. Okay, you can define functions with default parameter values. Okay, so that's a little bit like having these partially applied functions. In a sense, you can think of that's the default value for x, except I have to give it a name. So here I have to give the thing with the default value a different name. So partial application is not quite exactly like default values. But these are tricks that different programming languages have for doing various things. Default values act a little bit like partial applications, and partial applications look a little bit like default values. Python has default values, but not partial application. ML has partial application. Java doesn't have either. Java, this is what you would do in Java. In Java, if you wanted f with 4 for x, you'd have to give it a name, take a string for y, then you have to call f with that value. Okay? All right. So there's all kinds of neat things you could do with functions. There's all kinds of interesting, clever ideas that people come up with. Partial application only works with curried functions. Partial applications means you can give the function one of its inputs, but not all of its inputs. Okay. And like I say, we saw this is the classic use of it. Something like this, where you've got a general function extreme that's got a higher order function that parameterizes it. So this guy parameterizes this. So if you give this thing that, you've got a special case of extreme. And so you can give it a name. So max is the special case of extreme that uses the greater than parameter. And min is a special case of extreme that uses the less than operand. The operator uses the less than operator. And this uses the greater than operator. Okay. ML does this a lot in its libraries. Lots of functions in ML are actually special cases of more general functions, where you special case the function by giving the general function, which is curried, some of its input parameters. So you give the curried function some of its input. Here I gave it one of its input parameters, and that gives me a special case of it. Okay, so that's a very nice design pattern that a language like ML lets you have. Okay, so that's the thing that curried functions can do that tupled functions can't do. Curried functions have this ability to be partially applied. I mean, this is not a particularly important example of a partial application. You know, G takes in two numbers and multiplies them. G with 4 only needs one more number and it multiplies everything by 4. Okay, that's not especially useful, but it gives you an idea of what the idea, it shows you what the idea is. On the other hand, this one here is exactly what it's used for. Max is a special case of extreme. Min is a special case of extreme. And I don't have to rewrite any code. I don't go up here and I don't need to write out what max is. I don't have to write out what min is, even though it looks a lot like what extreme, you know, this code up here looks a lot like this code down here, because max and min are just a special case of extreme. In a well-designed language like ML, I can write the general purpose function and then recover special versions of it by partial applications, which is really useful. When people write multi-thousand line programs in languages like ML, they use this trick pretty often. It's a very common trick to write some very general purpose curried function and then recover specialized functions by partial application. The advantage is you only debug this one function. You debug that one general purpose function, and then you get several similar functions out of it that don't need any debugging. So this can be really useful in a large library. If you can do this several times, if you can write a general purpose function and get 2 or 3 special functions out of it, then you're cutting your code base by half or a third. Even if you get 2, you write this general purpose function and you get 2 special cases out of it, you've cut your code in half. You only debug one general purpose function, and you get 2 special cases out of it. And you could potentially get other special cases out of it also. Like here, longest and shortest are partial applications of extreme. This found the longest string in a list of strings. This found the shortest string in a list of strings. And they were partial applications of extreme. Okay. Library designers in ML do this all the time. Write some fairly general purpose function that's curried, and then feed it just some of its parameters and get very useful special cases. And it's not unusual for the general purpose function not be what you want. The general purpose function may even remain hidden inside of the library, and the library only exports the special cases. The general purpose function might actually only be there to make the code in the library smaller, so that you only debug one general purpose function, but then you build a lot of special cases out of it. And it might not be unusual in a library to have a very general purpose complicated function like this that's not even exported from the library. It's just hidden in the library for the developer's use. But then they export, say, 3 or 4 special cases of this that are really what they're interested in. But then they only maintain that one function. And then they just get these one-line definitions of the special case functions, which don't need to be debugged, okay? And don't need to be maintained, okay? So currying is real useful for this purpose. All right, so now we know that from now on, when we read a function definition, if you see commas, those are tuples. And that means the function takes in a tuple. If the function is going to take in multiple parameters, you look for spaces. See, space between two things. That's two parameters. Okay. I could do some funny examples like here. I'll just do a function h, and it'll have a tuple, a number, uh, okay. There's a function of 4. There's 4 inputs. 1, 2, 3, 4. So the function actually has 4 inputs. A, a, well, right now, this is a tuple. This is a thing by itself. Don't really know what it is. It depends on what we do with it. This is a triple. We don't know what that's a triple of yet until I define something on the right-hand side. So, for example, let me do this. X, constant to Y, constant to A, constant to B, constant to C, constant to W. Okay? What that means is W is a list, and then these 3 things are going to be put at the front of the list, then this thing's going to be put in front of those 2, and this will be put in front. So this will be a list of A, this will be a triple of A's, a single A, and a pair of A's. Okay, and this will be a list of A's. Okay, so the function will take in 4 things. I can go over here and give this to ML. And it's just a kind of a quirky example. Okay, but read it carefully. Read the output. It's a function that takes in a pair of A's. See, so that's the first input. Up to the first arrow, the first input's a pair of A's. Then the second input is a B. Okay, why does it end up being a B? Did I forget to use it? Oh, I forgot to use the Z. I forgot to put the Z in the list. Oh, notice that since I forgot to use it on the right-hand side, it's got its own type. I meant to put that in, so let me see, where would it go? It would go right here. The Z would go right there. Okay, so I want to put all those things in the list. Okay, so takes in a pair of A's, then it takes in one A by itself, then it takes in a triple of A's, then it takes in a list of A's, and it produces a list of A's. Okay, so you count the arrows. 1, 2, 3, 4 arrows means 4 inputs, and the last thing is the output. So 4 arrows means 4 inputs. 3 arrows would mean 3 inputs. 1 arrow would mean 1 input. So this is currying. So a pair, an item, a triple, a list, and then the output. Okay, so 4 inputs. Okay, and I can let me do a slight variation on that. Let's take the X and Y and cons them onto Z, but make Z its own list. Okay, so take X and Y and cons them onto Z, and then return a pair of lists. Okay, just make things a little bit. Let's read what this will be. So this will take the X and Y and cons them onto the Z, which is a list, and it'll take the A, B, and C and cons them onto W, which is a list. So Z is a list, W is a list, the X and Y are const onto Z, and the A, B, and C are const onto W. Now, since there's no feedback between this and this will be of one type, and this will be of a different type. So this will be a pair of A's and a list of A's, a triple of B's, and a list of B's. And the output will be a pair made up of a list of A's and a list of B's. Okay? Okay. So here we're playing around, we're polymorphism, typing, currying, triples. We're doing a little bit of everything in this one example. My key is really, my Now, 1, 2, 3, 4 arrows tells me that there's 4 inputs. The thing was long enough that ML broke it up into 2 lines. The first input is a pair of A's. The second input is a list of A's. The third input's a triple of B's. The fourth input is a list of B's. And then this tells me what the output is. The last arrow tells me the output. The output is a pair, list A, list B. Okay. And then I could call H with, say, 1, 2. Well, actually, make it, say, cat, dog. Put those on the empty list. And 3, 4, 5. Put them in the list 7, 8, 9. Oh, I forgot. I put a quote here instead of a semicolon. So let me just. Okay. Oh, I forgot to close the string dog too. So I had a couple typos. Okay. So there's the pair cat and dog constant to the empty string. So I got the string cat dog, and then 3, 4, and 5 were constant in front of 7, 8, and 9. Right. All right. So I got out a string list and an int list. Okay. But notice that the key is to start learning how to read these, how to read curried functions. Okay. The arrows separate the inputs. So however many arrows are in this signature, that's how many inputs there are. The last arrow tells you what the output type is. Okay. So the inputs are separated by arrows. And remember, this function is curried. So I could, if I wanted to, give it just that one input. So I could take this function here, h, and do something weird with it. I could define a function val h2 equal h with cat dog. Okay. Okay. Now h2 is kind of funny. H2 has got the two things that concatenate on a string list. So here's a string list. Okay. So cat dog are going to be put in front of apples. Okay. And then I have to do the rest of the input. I need a triple of something and a list. Okay. Okay. Oh, what did I do wrong here? Oh, I didn't like my definition of FH2. Did I do something wrong? I know you did something wrong up here. Oh, it didn't like that empty list there. Oh, no, that wasn't it. No. No, something went wrong with, I'm not sure what went wrong with this definition here. Let's see. H2. Yeah, H2's got a bizarre type. Something's wrong with H2. So I have to go back and think about that. I don't know what offhand, I'm not sure what I did wrong there. But you can see that H2's got a bizarre type. That's not a proper type. So something went wrong when I tried to do the partial application of H2. Does anybody see, can anybody see something obvious I did wrong? I don't see it yet. I don't see, I was trying to do just that partial application. I'm not sure what I did wrong. Okay, But let's go on to something else. They'll figure that out later. Okay. So something, I've just goofed up something. But notice that if you get these funny type signatures with capital letters in them and question marks, those mean something went wrong. ML couldn't figure out the type of what you're working with. And it just, it's like notice it's not a compiler error. It's just a funny type, but it's a type that's not useful. But the warning was up here. So I got an error up here, and I got left with H2 having a funny type. I should have paid attention to this error. The H2 wasn't defined properly, but H2 is left with this funny type. So H2 gets left with a weird type. All right. So now now that we've spent a lot of time talking about currying, let's go back to talking about higher order functions. And now we can start using a currying. We're gonna use currying from now on. Okay, so we'll make a lot of use of currying. Now, here's what I want to show you a couple examples we're going to look at. Earlier in the semester, we did problems. Here's a kind of problem that we did before, where I give you a type signature and you have to write something with that type signature. See, here's a type signature, and you have to write a definition that has that signature. We did a bunch of examples like that early in the semester. Now here, all these type signatures are higher order functions. They're curried higher order functions. So this function takes in, see, it's got 2 arrows. Now be careful of that arrow. See, it's grouped. So this is a signature of the function takes in 2 inputs, an int and a function. So it's a higher order function. See, the parentheses here say that's an input to this function. If I got rid of that pair of parentheses, this would be a function of 1, 2, 3 inputs. It will be a function. So there's 1, 2, 3 arrows. But the way it was given, one of the arrows was in a group. So this is all of one input. So it's grouped together. So there's only 2 arrows. So the function takes in a function and an integer. And it takes in a function from integer to a. So the function takes in a function from integer to a, and it takes in an integer, and it's supposed to give me an a output. The question is, how can I define this function? I just know the signature. I have to come up with a function that has that signature by thinking, well, I'm given a function h, that's this guy, which goes from int to a, and I'm given an integer n, and I have to produce, now here's my output, I have to produce an object of type a. Okay, again, I have a function from int to a, and I have an int, and I need an a. Well, the most thing to do is apply the function to the int. Notice it looks kind of weird, hn, hn, but this is input function h, input number n, and now I need to produce an output a of type a. But h is a function from int to a, so just give it that. Okay, that's my answer. Okay, we're out of time. Let me just put that into ML and show you that. Okay, now see, that has the type I wanted. Oh, it actually is more general than what I wanted. Okay, it's more general than what I wanted it to be. Notice I got a function from A to B, takes in an A and gives me out B. To make it actually say that this is an int, I actually have to say that that's an int. Because otherwise, I didn't do anything. Now I could, I wanted this thing to be an int, so I could just say, okay, it is an int. Okay, see, now I got a function from int to a, an int, and now an a. So I got the signature I wanted. I have to do something to make ML realize that this guy is an int. So another thing I could do would be, here's another thing I could do. F1 Hn is h of 1 plus n. Now, by adding 1 to n, I'm forcing it to be an integer. Okay, so then instead of declaring it to be an integer, I could cheat and add 1 to it, and that forces it to be an integer. So now that will have the signature I want. Okay, so the game is give you a signature. They're all higher order curried functions. So every one of these functions has an input that is some kind of function. See, every one of them has an input that's some kind of function. And they're all curried, so they all take at least 2 inputs. Okay? Except, oh, this one's not curried. Well, this one only takes in 1 input, but the 1 input is a function. So this is a function that takes in a function and gives me back a b. Okay, and the question is, this one's going to be a little bit tricky. It only has 1 input, so it's not curried because it only has 1 input. So it takes in a function from a list of A to a B item, and it wants me to give back just the B item. Okay, so I have to cook up something that'll do that. This one's curried, takes in a function and an A, and gives me back a B. Okay, this one's not curried. See, it's only got 1 arrow in it. So what it takes in is, this is a tupled function. See, it takes in a pair. And it's a function and a list in a pair, and it's supposed to give me out a B. Okay, so it's a higher order tupled function, not a curried function. It takes in 1 input that's a tuple, but one of the inputs in the tuple is a function. So it's a higher order tuple function. So we'll play with these on Thursday. We'll do a few of these, and this will give us a more of a sense of how ML works with higher order functions. And then then we'll be ready to do, see, today, what we did today was mostly, we spent a lot of time talking about this currying. We're going to spend, we'll go back, we're going to do some examples of higher order functions, and then we want to do these predefined higher order functions: map, fold, and filter. The important predefined filter functions: map, reduce, fold, filter. Okay, so we're going to do some examples. We'll do these type examples to get practice with thinking about higher order functions, and then we'll do the predefined ones. So we're spending a lot more time. This chapter's in the book. This chapter is short. I think the book spends very little time on very deep ideas. So we're spending a lot more time on this than you might think of from reading the book. The book is pretty terse, and it doesn't give that many examples. Like the explanation of curried is just like on 1 page. And I think a lot of people find it hard to understand what he's explaining, because he doesn't explain it in a lot of detail. So we did a lot more with curried functions today than what the book says, and we still have to figure out how they're defined. Okay, and then we're going to spend more time doing these predefined higher order functions than what the book does too. So we're going to this is the heart of the stuff on ML. It's the shortest chapter in the book, but it's actually the heart of where the real interesting part of ML comes up. Okay, so we'll quit there. We'll pick up with these on Thursday with these examples of these, because they're pretty interesting little problems. Okay, anybody got any last second question? Any last second question? Okay, so see you on Thursday. Bye.